Okay, we've been talking chapter 9 and stoichiometry, and at the end last time we got into the idea of limiting reagents. And the idea of limiting reagents, and there's also excess reagents. And the idea behind this is, again, if you have a reaction, oops, do that, maybe. When we react both of these reactants together, there's always one that's going to get used up first, and that is your limiting reagent, so that gets used up first. And let's just say, for example, the A here again was our limiting reagent. What that means is as soon as we sort of use up A, there's no possible way to make any more products at that point. And that's why limiting reagents are important to identify which one is the limiting reagent because it is the one that determines how much product you can make. So that one determines how much product you can make. Because again, as soon as that's sort of used up, there's really no chance of you making any more product. Now, the other reagent is the excess reagent, and the excess reagent you have plenty of, and you'll even have some left over when the reaction is done. Um, and you do need to identify, again, like I said, which one is the linear reagent. It does need to be identified through some type of calculation. You can't just look at the moles and go, that one's the smaller one, so that's going to be a linear reagent. So you actually have to do a calculation to determine that. We talked about really two ways that you could kind of do that, and there are multiple ways that you can kind of figure that out. But one way is really just the same sort of four steps that we use in a regular stoichiometry problem, which is balance the equation. You want to convert to moles. Then right around here, you'll do your sort of limiting reagent calculation. And what we're going to do in this case is just try to figure out how much of one reactant is needed to use up the other reactant. So in the step before, you definitely will have the starting moles of each reactant. And you could do this little calculation between the two reactants. And again, basically what you're trying to figure out is if I want to use up all of one of the reactants, how much of the other one I need to put in there. Then you would compare and see if you have enough. And if you do have enough, then that means that is the excess reagent. If you do not have enough, then that is going to be your limiting reagent. And once you make that determination, the rest of the steps are pretty much the same. You're going to use your limiting reagent to do the mole-to-mole relationship. You then will convert those moles into some other unit. So that is one approach that is used to sort of figure out limiting reagents. The other approach is really just doing two separate calculations, stoichiometry type calculations. One for each reactant that you're given. So the other method is sort of, thank you, is to just basically do two separate calculations going from the first reactant to the product, then from the second reactant to the product. And in this sort of method, whichever one produces the smaller amount of product is both your limiting reagent and your theoretical yield. So whichever one produces the least amount of product is both your limiting reagent and your theoretical yield in that case. So those are two very commonly sort of ways to do these type of problems. Questions on that here? All right, so I think we just talked about it sort of at the end there last time. So let's take a look at some examples here and see. Yeah, like them. All right, so we have 6.83 grams of iron reacts with 9.34 grams of sulfur. Which one's the two is the limiting reagent, and calculate the mass of iron 2 sulfide needed. So I'm going to give you some numbers here. Why don't you give it a go? Follow those steps there. Iron is 5585. Okay, let's take a look and see how you're doing. So in this case, we do want to follow our steps here. We are given the equation. We just want to make sure it's balanced, and it does look like it's balanced. When we look at what is given to us, we have the grams of iron and we have the grams of sulfur. So a reminder that in a lot of problems, or in most problems, they will not tell you, for example, it is a limiting reagent problem. You just have to know that it is. And this is one of the ways that you can know that it is. As we talked about, the way you know really this is a limiting reagent problem is you can get to moles of each reactant. So if you're ever given sort of a stoichiometry problem and the information given to you allows you to directly calculate the moles of each reactant, that is how you know you need to do a limiting reagent type problem. So clearly here we have the grams of iron and we have the grams of sulfur, which definitely we could get to moles super easy. And that tells us this is a limiting reagent problem. So we could follow our steps here again with the limiting reagent sort of part in it. So first one is balance. Second one is we're just going to convert everybody into moles. So to get to the moles of iron, we're going to take the 6.83 grams of iron. We're going to go to the periodic table, use the molar mass, 5585 grams per mole. Grams on the bottom so they cancel. And that is going to get us there. Looks like 6.83 divided by 5585. Going to get us a 0.122, I'll call it 3 moles of iron. We'll do the exact same thing for our other reactant, which is sulfur. So we got 9.34 grams of sulfur using the molar mass from the periodic table for sulfur, 3207 grams per mole. Again, the grams are going to cancel. And that will get us 9.34 divided by 3207. Going to get us 0.291, we'll call it 3. One, actually 2. So 2912 looks good. Moles of sulfur in this case. Any questions on that so far? So just really just a conversion of grams to moles using the molar mass from the periodic table. All right, so we want to think about these two values as really our starting amounts of each of these, right? So these are basically what we're going to start with. So because we have identified that it is a limiting reagent problem, we do need to do our limiting reagent calculation. Again, a reminder that you cannot just go by the moles here and figure out which one's the smallest. You do have to do some type of calculation. So I'm going to figure out my limiting reagent by doing that calculation. And again, it's a calculation between our two reactants. And basically what we're trying to figure out is if I want to use up all one reactant, how much of the other one is needed. So in this case, I'm going to try to figure out how much sulfur is needed to use up all the iron I started with. So I'm going to take the moles of iron that I started with, 0.1223 moles of iron. I'm going to go to the equation and find my mole-to-mole relationship between the two reactants. And I can see for every 1 mole of iron, I get 1 mole of sulfur. So that's not too bad. So we're going to go 1 mole of sulfur up on top, 1 mole of iron on the bottom. That's going to cancel out the iron and tell me I need 0.1223 moles of sulfur is needed. So once again, this is just a calculation to figure out which one is the limiting reagent. Now, once I do have this number, I want to compare it to how much sulfur I am starting with. So in this case, I need 0.122 moles of sulfur. I am starting with 0.29 moles of sulfur. Do I have enough sulfur in this case? I do, right? I only need 0.12 and I have 0.29. So I have enough. And right there, when you determine that, because you have enough sulfur, that will tell you that the sulfur here is our excess reagent, and our limiting reagent in this reaction would be the iron. Now, if you were to compare that and you did not have enough, then that would mean that reagent would be your limiting reagent. So that is, again, how you can determine it. Any questions on that there? The good news is you just have to determine one. If you could determine something is the excess, then the other thing is the limiting, or vice versa. If you know that's the limiting, then the other guy is the excess. Any questions on that? All right, so now that I know that my sulfur here, I'm sorry, my iron here is my limiting reagent, I can now just basically pick up the problem like normal and just start here with step number 3. And you want to use your limiting reagent now. So we're going to go this way. So now we're going to go step number 3 here, using our limiting reagent to our product. And you want to make sure that you go back and use the starting amount there of your limiting reagent, which is 0.1223 moles of iron. We now can do the relationship between iron and our product. And we can see that in this equation, for every 1 mole of iron, there is 1 mole of iron 2 sulfide. So we'll use that as our conversion factor here. 1 mole of iron, 1 mole of iron 2 sulfide. That gives me 0.1223 moles of iron 2 sulfide, as those guys will cancel. In this case, we're not looking for moles, but if we were, that would be the answer. Maybe clean up some sig figs on it, but that would be our theoretical yield in moles. But we do want grams, so the 4th step is we're going to go from moles, in this case, to grams. We will need the molar mass of FeS, so we're just going to add those together. So that's going to give us 5585 plus 3207. That's going to give us a molar mass of 8792. So the last part here is we will use that molar mass to convert our moles into grams. And if we do that, 0.1223, looks like we will produce somewhere in the ballpark there of 10.8 grams of iron 2 sulfide. That is our theoretical yield in grams in this case. Any questions on that there? Now, another thing that we talked about last time as well is sometimes you are asked how much of that excess reagent do you still have left over. So for example here, just clear up some space. If we wanted to know, or we were asked how much of that excess reagent's left over, we can do a calculation between the two reactants and use our excess reagent there and figure out how much is needed. And that is what we did here. We basically figured out, since we chose kind of luckily here, that guy, we figured out that we needed 0.1223 moles of sulfur. We had 0.29 moles of sulfur to start with. So in this case, the moles of sulfur that's left over, which is our excess reagent, would be our starting amount of sulfur, 0.2912 moles. Again, that's kind of what we started with. We did our calculation here earlier that told us how much we needed, which was 0.1223 moles needed. And if we subtract those two, that will tell us how many moles are left over. We have approximately 0.1689 moles of sulfur that's left over. And again, if we want to know how many grams that would be, we could use the molar mass of sulfur. And those will cancel. And that would equate to approximately 5.42 grams of sulfur is left over. So we started with about 9.34 grams of sulfur. In this case, we got about 5.4 left over. So roughly we used about 4 grams or so in this reaction, and we still have about 5 or so grams basically of that left over. Obviously, for our limiting reagent, we will have 0 left over because it gets completely used up. So you should have none of that left over. Any questions on that there? Now, we happen to have gotten lucky based on this calculation that we use to figure out which one's the limiting reagent. If you did not do that calculation but did the other one, you would then have to come back and do this calculation to figure out how much is left over. So sometimes you get lucky based on which one you choose to figure that excess reagent. Otherwise, you have to go back and kind of do that calculation if you didn't do it. Any questions on that there? You definitely would have to go back and do it if you did kind of the other method of solving this. You'd have to go back and definitely do that calculation. All right. All right, let's try another one here. If you take 622.7 grams of NH3 and they give you the molar mass, 1703 grams per mole, and you react it with 1,241 grams of CO2, molar mass 4401, how much? Okay, so let's take a look, see how you're doing. So again, in this case here, we have an equation. We're going to react 622.7 grams of NH3, and they were nice enough to give you the molar mass of 1703 grams per mole, with 1,241 grams of CO2. Also gave you the molar mass 4401 for that. We're looking for how many grams of our product. So once again, this is a stoichiometry problem. This also is a limiting reagent problem. Again, they may not always tell you, and they definitely will not tell you usually in most cases. I know that because I have grams of NH3, which means I could get to moles, and I have grams of CO2, which also means I could get to moles. So because, again, you could get the moles of each of the starting reactants, you know this is a limiting reagent problem because of that. So again, somewhere along the way there, you need to determine which one's the limiting reagent. Good news is pretty much first two steps are always the same regardless of what method you choose. So we want a balanced equation, which we have. We then want to convert everybody into moles. So we'll start with the NH3. So we have 622.7 grams of NH3. They gave you the molar mass in this case. If they didn't, you would have to obviously go to the periodic table to get that 1703 grams per mole. Again, the grams are going to cancel, and that will get us here 622.7 divided by 1703. Going to get us 36.608 moles of NH3. We'll do the same thing for the other reactant, which is 1241 grams of CO2. Also gave you the molar mass. So again, if they did not, you would have to go to the periodic table and calculate it yourself. CO2 grams are going to cancel. So 1241 divided by 4401 going to get us 28.198 moles of CO2. Once again, you can think of these as your starting amount. And because it is a limiting reagent problem, as we talked about previously, we will need to do a calculation. So in this case, I'm going to calculate how much CO2 is needed to use up all the NH3 that I started with. So again, this is just a simple little calculation between the two reactants to help us decide which one's the limiting reagent. So I'll take all my NH3 moles, 36.608 moles of NH3. I'm going to go to the equation and find the relationship between NH3 and the other reactant. And from the equation, I can see for every 2 moles of NH3, I get 1 mole, mole of CO2 there. And we're going to use that as a conversion factor. So 2 moles of NH3 on the bottom, my 1 mole of CO2 up on top. Moles of NH3 will cancel. And this is going to tell me here 36,608 divided by 2, that 18.304 moles of CO2 are needed. So again, this calculation is to determine which one is our limiting reagent type of deal, right? So we're going to now compare the CO2 that is needed to the CO2 that is starting with. Here I'm starting with 28 moles and I only need 18 moles. So here again, I do have enough. So I have enough. And because I do have enough, that again means that the CO2 here is my excess reagent. And the limiting reagent in this case would be the other one, which would be the NH3. Any questions on that there? So again, now that I have determined the limiting reagent, I'm ready really to finish kind of the problem here. We are going to start with our limiting reagent and now go to our product, basically. So using the starting amount of our limiting reagent, which is 36.608 moles of NH3, we can now do the relationship between NH3 and our product. And we see from the equation for every 2 moles of NH3, we get 1 mole of our product here. And again, that is just the coefficients in the balance equation. So using that as a conversion factor, for every 2 moles of NH3, we get 1 mole of our product. And we will end up here with 18.304 moles of our product. And that would be our theoretical yield in moles. But we are looking for grams. So the last thing we need to do is take those moles that we just calculated there and convert them into grams using the molar mass. Once again, they were nice enough to give that to us. Looks like it was 6006. Again, like normal, if you were not given it, you would need to calculate it yourself from the periodic table. Moles are going to cancel, and we'll take that times 6006. Gives us approximately 1099 grams of our product here. It looks like everybody's about 4 sig figs, so that would probably be all right in this case. And this would be our theoretical yield in grams. Yeah, so that'll be our theoretical yield in grams. Any questions on that there? Hopefully you can see it is kind of the same 4 steps as a basic stoichiometry problem. You just sort of in the middle there got to do that small little calculation to figure out which one's the limiting reagent. And the important thing is after you do that to continue on with the starting amount of limiting reagent to finish out the problem. Any questions on any part of that there? Okay. All right, so we've been kind of talking about some yields here and a reminder that a yield is a product and should always be a product. It's basically what is formed as a result of the reaction. And let's talk a little bit about different types of yields that we've sort of been touching upon. Here's this one more time. And in this case, we didn't do the calculation together, but again, we could also, like previously, figure out how much of our excess reagent was left over by subtracting how many moles of our excess was needed versus how many moles that we started with. So that's what we started with. That was our calculation, I think, of what we needed. And that will then tell us how many moles are left over. And then that could get converted into grams that were left over as well. All right. So speaking of yields, there are three types of yields that we come across. And one is the theoretical yield. And the theoretical yield is what we've been calculating. The theoretical yield is your maximum yield. It is based on the balanced equation and what you're starting with. And the theoretical yield is your maximum yield because ideally, if everything went perfect, you didn't lose anything along the way when you did the experiment, there was like no side reactions or anything like that. That is how much you should produce in that reaction. So if everything went perfect based on the equation, based on what you're starting with, you would be able to figure out how much maximum you should be able to get. In most cases, the theoretical yield is calculated. And that means that you typically need to calculate the theoretical yield. That could be just a basic stoichiometry problem. That could be a limiting reagent type of stoichiometry problem. But usually you do have to calculate that theoretical yield. Now, the actual yield is the amount of product you actually get when you do the reaction. So the actual yield is, again, how much you actually produce when you do that reaction. In textbook problems and stuff like that, and in most cases, that is usually given to you in a problem, unless you're physically doing the experiment yourself. But if you're doing some type of textbook problem, that is usually given to you somewhere in the problem. Somewhere in the problem, they'll tell you how much of the product you produced. Once again, obviously, if you're doing the experiment, you would get that yourself or figure it out yourself. Now, we use both of these yields to calculate an important number, which is known as the percent yield. And the percent yield is taking the actual yield divided by the theoretical yield times 100%. Now, percent yield, we ideally want a big number. So close to 100 is great, so high 90s, mid 90s is really good. And that's ideally what we're shooting for. We definitely, in most cases, do not want over 100%. And it can happen. And it can happen, for example, like the experiment we're going to do today, where you make a precipitate and you kind of dry it out. And for example, if you did not completely dry your precipitate, when you go reweigh it, you're going to have more mass than you should because it's water weight. So you got this extra water weight that you're going to count as actual yield. And that's going to, again, make you end up with over 100%. So usually if you go way over 100% or over 100% yield, it's usually not a good thing. Usually something not so great happen. You do want to kind of get as close to 100 as you can. It's really good. So we don't want usually a small percent yield. So actual divided by theoretical times 100. Now, in terms of the units for the actual yield or the theoretical yield, it really doesn't matter. So you could do grams over grams. They do have to be the same on top and bottom. You could also do, if you wanted to, since sometimes you maybe just have the moles, you could divide moles divided by moles too. So as long as your theoretical yield and your actual yield are in the same units, you could divide them and times it by 100 and get the percent yield. So sometimes people think they always got to be in grams and grams. They don't, as long as they are the same units, though. They do have to be the same units in order for it to work. All right, so why don't we try one here, maybe. Why not? All right, I want to try this one here. We have 2.46 times 10 to the fourth kilograms of TiCl4. Molar mass is 189.7 grams per mole. Reacts with 1.44 times 10 to the 4 kilograms of magnesium. Molar mass 24.31. What is the theoretical yield of Ti in kilograms? And what is the percent yield if we produced 5.42 times 10 to the 3? Okay, let's take a look and see how you're doing. So in this case, we're looking for the percent yield. So again, our percent yield is our actual divided by our theoretical times 100%. In this particular case, we do have the actual given to us in the problem, and that is the 5.42 times 10 to the 3 kilograms that were produced. And again, usually the actual yield is given to you, like I said before, in a textbook problem. Now, the theoretical yield, we actually do need to calculate in this case. So that's going to be a stoichiometry problem. When I look at this, I have kilograms of the TiCl4, which definitely I could go to grams and also then go to moles. I also have kilograms of the magnesium, which again also means I could go to grams and then to moles. So once again, I have the ability to get to moles of each of these reactants. So that is going to tell me this is a limiting reagent problem, and I am going to have to sort of figure that out along the way. So we will start with our equation, which looks balanced. So the next thing we're going to do is just like normal, going to take what they gave us and convert them into moles. So in this case, we got 2.46 times 10 to the 4 kilograms of TiCl4. I'm going to convert the kilograms into grams. So in 1 kilogram, there's 1,000 grams. Then I'm going to now use the molar mass that was given to us to convert those grams into moles here of TiCl4. So kilograms cancel, grams cancel, multiplying the top, dividing by the bottom, and that's going to get me 2.46 to the fourth, wherever that went. Where did it go? There it is. To the fourth times 1,000 divided by 189.7. And in this case, that's going to get me, looks like, we'll go here, 1 point, I'll call it 30 times 10 to the fifth moles of TiCl4. We'll do a similar calculation for our other reactant, which happens to be in kilograms as well, 1.44 times 10 to the 4 kilograms of magnesium. Again, first converting our kilograms into grams so that we could use our molar mass properly, which was also given to us here, 2431 grams per mole. Kilograms cancel, grams cancel, leaves us with moles. And that's going to get us here 1.44 to the fourth times 1,000 divided by 2431. Going to get us here 5.92 times 10 to the fifth moles of magnesium. This again, both of these are our starting amount of each of those. Any questions on that calculation there? Because it is a limiting reagent problem, we have to do our normal little calculation here to figure out our limiting reagent. So in this case, I'm going to figure out how much magnesium is needed. So in this case, I'm going to take my TiCl4, our 1.3 times 10 to the fifth moles of it. I am then going to go to the equation, do my mole-to-mole relationship between the two reactants. And from the equation, I can see for every 1 mole TiCl4, I get 2 moles of magnesium. So I'm going to use that to do this calculation. That means the moles of TiCl4 should go on the bottom, and the 2 moles of magnesium should go up on top. And that will tell me here that I need 1.3 to the 5 times 2. I need about 2.6 times 10 to the fifth moles of magnesium is needed in this case. Again, I'm going to compare that to how many moles of magnesium I started with. And in this case, I need 2.6, and I got 5.92. So again, here I do have enough And that would mean that the magnesium here is my excess reagent, and the TiCl4 would be my limiting reagent. Any questions on that there? Now that I know the TiCl4 is my limiting reagent in this case, we can finish up our problem here and figure out our theoretical yield. So kind of doing our third step, we again want to start with our initial amount there, 1.3 times 10 to the fifth moles of TiCl4. We can now go from our limiting reagent to our product, which happens to be a one-to-one relationship, which is pretty nice. So we're going to go 1 mole of TiCl4 from the equation gives us 1 mole of our product. And that's going to obviously give us the same number there, 1.3 times 10 to the fifth moles of Ti. Now using the molar mass here of Ti from the periodic table, 47.88 grams per mole, gives us here 1.3 to the 5 times 47.88. Gets us 6.22 times 10 to the 6 grams of Ti. By the way, this would be our theoretical yield in moles. This would be our theoretical yield in grams. But the problem is I should not leave it in grams because my actual yield is in kilograms. So I do want to convert it back to kilograms so that they are in the same unit. So we'll do that little conversion there, 6.22 times 10 to the 6 grams. And there are 1,000 grams in a kilogram. And that's going to get me, dividing this by 1,000, 6.22 times 10 to the 3 kilograms of Ti. That would be my theoretical yield in kilograms. Question on that there so far? Yeah. Are you talking about this calculation here? Or yeah? And you're asking, can you do what now? You have to actually do this calculation. Um, so this calculation basically is saying if I wanted to use up all of the TiCl4, this is how much of the magnesium I would have to put in there. So you have to do this calculation. You cannot go if your question is can you go by like the numbers before you do that calculation to figure it out? You can't. You have to actually do a calculation to figure out which one's the limiting reagent. Yeah. You could, if your question is, could you use the moles of magnesium, figured out how much TiCl4 you needed? You could do that. So that's the other sort of calculation you could have done. Okay. Because you cannot use the grams, so you have to do or kilograms. You have to do some type of mole to mole. Okay. Okay. So this is your theoretical yield. We do have our actual yield. They're both in the same units. So that's going to allow you to calculate the percent yield. So we'll take the actual, which was given to us, 5.42 times 10 to the 3 kilograms. We'll divide it by the theoretical and times it by 100%. And in this case here, we will end up with times by 100. And it looks like we'll end up with about 87.1% yield. Not terrible, but definitely at least under 100, so that's good as well. Any questions on that there? So again, as we talked about, this one is an example as well of you may not always just be given grams to begin with. You may be given some other unit. So you do have to get them to grams and then get them to moles. You do need to, again, do a calculation to figure out which one's the limiting reagent. And in terms of percent yield, you can use different units to calculate percent yield as long as the actual yield and theoretical yield are both in the same units. You could do that. So in this case, we did kilograms over kilograms. We could have also done grams over grams if we converted our actual to grams. And we could have also done moles over moles if we converted our actual into moles. So as long as the actual and theoretical are the same units, you could divide them out to get the percent yield. Questions on that there? All right, we will lay it up there for now.